In this video, we're going to talk about what happens when you want to calculate the matrix exponential for a 2 by 2 matrix with complex eigenvalues. So one of the things that's a useful fact to know is that suppose that you have a matrix A and you can write it in the form P, C, P inverse, where P is some invertible matrix. So suppose you have a matrix A and it has this matrix decomposition or matrix factorization. Then the matrix exponential e to the at is equal to P times e to the ct times P inverse. Okay, so the proof of this is an exercise. Oops, how did I do that? And maybe in another video I will explain why, but you really do just write out the definition of e to the at as an infinite series, and then you use the fact that A can be written as PCP inverse, and then you just factor out the P on the left and the P inverse on the right, and then you see that what you get in the middle is e to the CT. And I basically just explained how you prove it. So not a terribly complicated fact. So we're assuming also that all the series converge, right? So we don't have these issues of the infinite series diverging to infinity or anything like that. Okay, so when does A equal PCP inverse? Well, actually, it turns out that every square matrix can be written as PCP inverse. That's a theorem called the Jordan form. There's something called the Jordan form. And the matrix C in the Jordan form is this, it's almost diagonal, but there might be ones directly above the diagonal entries, or there might be ones directly below the diagonal entries, either one or the other. It kind of just depends on your convention for whether you want the ones above or below the diagonal. If your matrix is diagonalizable, so that's when C is a diagonal matrix, right? And we know how to exponentiate a diagonal matrix. It's just e to the diagonal matrix times t, if you're doing e to the dt, on the main diagonal. Okay, so in a previous video on the matrix exponential, I explained why that's true. That also just follows immediately from the definitions, so not something terribly complicated. Suppose now that you have a 2 by 2 matrix with complex conjugate eigenvalues. So suppose that A, so here's the theorem we're going to use. Suppose that A is a 2 by 2 matrix, so 2 by 2 real matrix. Real matrix meaning the entries are real numbers, not complex numbers, or not, oopsie. Oh, no, I don't want this. Okay, a 2 by 2 matrix with real entries, so not non-real complex numbers, right? No imaginary part. So suppose A is a 2 by 2 real matrix. Well, suppose it has complex eigenvalues, so non-real eigenvalues. Well, if they're non-real, then they have to be complex conjugate, so complex conjugate eigenvalues. Let's call them lambda equals A plus BI, and lambda bar equals the complex conjugate A minus BI. So A and B are real numbers. Okay. Then the theorem says that there is a matrix, an invertible matrix, P, such that A is equal to P times this matrix. The first column is A negative B, and the second column is BA, P inverse. So why do we want to work with P, C, P inverse? Well, because we've seen that the matrix exponential e to the at solves the differential equation x prime equals ax. So you want to calculate e to the at. And if you can write A as PCP inverse, we see from this fact above that you can calculate e to the AT as long as you know what P is and as long as you know e to the CT, right? Because of this. So the point is that often you can write A equals PCP inverse, where C is something that is easier to calculate the matrix exponential of. So if your matrix is diagonalizable, your C is a diagonal matrix, and it's easy to exponentiate a diagonal matrix. And for the theorem here, when you have a 2 by 2 real matrix with complex conjugate eigenvalues, this matrix C turns out to have a nice exponential. So once I prove this theorem, okay, so I tell you how to find the P. Okay, the A and the B come from the eigenvalues, right? Lambda and lambda bar. Okay, it's just the real imaginary parts of lambda. After I prove this, then we're going to talk about how to find e to the CT. And e to the CT has a very nice answer. And once you know the answer, then you can find e to the AT, because it's just P e to the CT times P inverse. And that's what we're going to do. All right, so how do we prove this theorem? Well, I have to tell you what P is, and then I have to explain why A equals PCP inverse. So the way it works is, suppose you take an eigenvector of lambda. So an eigenvector with eigenvalue lambda. So let phi be an eigenvector of lambda. Now usually phi will have complex components. So complex, usually, eigenvector with eigenvalue lambda. So phi is this vector that has two components, and then the components might be complex numbers in general. In general, they're complex numbers. So what you can do is we can write phi as u plus iv, where u and v are real numbers. Okay, so u plus iv, where u and v are vectors in R2. Right, we're just splitting it into the real and imaginary parts. Okay, so now let's calculate A times phi. Well, phi is u plus iv, and since phi is an eigenvector of the matrix A, this is with eigenvalue lambda, and lambda was A plus bi. A times u plus iv is going to be A plus bi times u plus iv. So A and B are real numbers, u and v are vectors, right? But when you're multiplying a number by a vector, you just multiply each of the components by that number. So this is going to expand to A times u. Let's look at the real part. So to find the real part, you take A times u, so A and B are real numbers, right? And then you have bi times iv, and iv is gonna, you have I times I, and that's -1. So you're going to get au minus bv. That's the real part of this vector, and then you have the imaginary parts, so this plus I times, and then you have the imaginary part by doing A times IV and then BI times U, right? That's going to give you the imaginary part. You factor out the U, so that gives you you factor out the I, so that gives you AV plus BU. Okay? So that's what A times phi is equal to. But we also have A times U plus IV, so that's A times phi. We have the linearity of matrix vector multiplication. is going to be A times U plus I times A times V. You just multiply the real part and the imaginary part. So now we have two expressions for A times U plus IV. So these two, this and this, these are the same because they're both A times phi. So we can set the real and imaginary parts equal. So set real and imaginary parts equal. So the real parts, when you set the real part, okay, if you look at the real part of the first one, it's this. The real part of the second one is that. So we're going to get AU equals AU minus BV. Now you look at the imaginary parts, it's AV and AV plus BU. So capital AV equals little AV plus BU. Let's write it as BU plus AV. So now we have these two equations, which we know are true. Now let's look at A times, so take the vectors U and V and put them as columns of a matrix. A times the matrix whose columns are U and V. Well, this is just the matrix whose columns are AU and AV. Because remember, when you have a matrix and then you multiply by a matrix on the right, you take your matrix A and then you multiply by the individual columns. And those give you the columns of the product, right? So this is going to be the matrix where the first vector, the first column vector is AU, the second column is AV. Okay, now let's also look at the matrix UV, the matrix whose columns are U and V, and multiply it by this matrix A, negative B, BA. Well, now we are using the fact that when you have a matrix and then you multiply by a matrix on the right, another way of thinking about matrix multiplication is that you're taking linear combinations of the columns. Okay, do you remember? Hopefully you remember this from when you took linear algebra. So if you want to multiply these two matrices together, okay, the first column is going to be the matrix here times this column, right? And when you take a matrix and multiply by a vector, one way to think about that is that that vector is telling you what linear combination of the columns of the matrix to take. So the result, when you take this matrix, whose columns are U and V, and then multiply by this column vector A minus B, the first column is going to be AU plus negative BV, so AU minus BV. Okay, so go back and review this fact that matrix times a vector is a linear combination of the columns of the matrix, if this is unfamiliar to you. And then, likewise, the second column is going to be BU plus AV, right? Because you take this times that plus this times that. Oops. Well, what do you notice? These two matrices, this matrix and this matrix, AU is equal to AU minus BV. So this column is the same as that column. This second equation tells you that this second column equals the second column. So that means that these two matrices are the same. So that tells you that A times this matrix, whose columns are U and V, equals the matrix whose columns are U and V times this matrix whose columns are A negative B and BA. And now I think you can see where the final ingredient is. You call this matrix P, this is P, that's your C, and now you multiply on the right by P inverse. So A is equal to P times this matrix times P inverse. And that's the proof. So let's go back and review how you find P. Okay, so you get your A and your B, your little a and your little b. Those are the real and imaginary parts of one of the complex eigenvalues. And it doesn't matter which complex eigenvalue you use. And then it's just that you want an eigenvector with that complex eigenvalue that you picked. So you call that eigenvector phi. You write out the real and imaginary parts, u and v, and then the columns of P are just u and v. And we showed that A equals P times this matrix C times P inverse. Okay, that's a pretty long video, I think, so I'm going to stop here, but in the next video I'm going to explain. So let's review where we are. So we wrote down A equals P CP inverse. So to find, and we know how to find P, right? So to find e to the at, and why do we want to find e to the at? Because it solves the matrix differential equation x prime equals ax, right? The columns of e to the at give you the solution space. So to find e to the at, we just need to find P, which we know how to do because we know how to find the eigenvalues and we know how to find the eigenvectors. So we just need P, okay, well, I explained this is easy. And we need e to the ct, where c is this matrix.